Assalamu alaikum. Assalamu alaikum wa rahmatullahi wa barakatuh. Today, inshallah, we will continue our lectures about heterogeneous catalysis and its impact or its use in water treatment and pollution in general. Last times we introduced some basic ideas about catalysis, and yesterday we talked about characterization of the catalyst, physical characterization of the catalyst or solid materials. Today, inshallah, we will talk about a very interesting topic as well. It is the in situ characterization of heterogeneous reactions. But basically, I want to explain the term, which is in situ. We have two terms, in situ and ex situ. What's in situ and what's ex situ? In situ, which is this one, which is the treatment, characterization of the catalyst at the time of reaction or at the real conditions of the reaction. However, ex situ means you after the reaction or after treatment, you take the sample and in air, of course, and whatever you will put it on your desk or on your shelf or on your bucket, whatever it is, it doesn't matter. It means it is not the real conditions which was there at the reaction time, okay, or at the heat treatment or something. Again, I'll tell you what's in situ. If you make a reaction and inside the reaction, the surface has undergoing several factors like heat and gases on the surface or liquid or vacuum, whatever its conditions. These are the real conditions which is the surface undergoes. But if you take the sample out of vacuum, for example, or out of reaction, it is not real conditions. It is not real conditions. Like if you heat the sample at, for example, 300 degree, 400 degree, whatever, it's in the oven, it has certain conditions. You take it from the oven, how much the degree will be? Maybe 25, 30. Is it the same conditions that you are, the same conditions of the sample when it is in the oven or in the heater? I think no. I am sure it is not the same conditions. Today, inshallah, of course, I'd like to say that all the instruments that were used yesterday, or we talked about it yesterday, can be used to characterize the catalyst in its time, in its heating or treatment time. But actually, we don't use it or we don't do this. But we can use the in situ technique in following up of the reaction. I'll show you some data, but let me, of course, let me tell you which this is the in situ that we just talked about now. There is a big difference between in situ and ex situ, and then in situ means we are characterizing or checking the catalyst at real time. It's real time observation or real time monitoring. Okay. Of course, we can just this is an introductory about how can we deal with a catalyst. Actually, there are two dimensions or three dimensions. The first dimension is the time. This is the first, but we will talk about the scale, the distance or the scale, which is it, are you talking about treating or monitoring the reaction at nanoscale, or you are talking about treating the reaction at microscale, or treating the catalyst or monitoring the process at macro scale? It is very different. Let's see here. The most important part is, this is the most important part. Many people just said that catalysis itself, without preparing nanomaterials, catalysis itself is a nanoscience. How comes? Because catalysis is dealing with the reaction in the nanoscale, where, of course, you are talking about molecule is absorbed on active site and is reacting with another molecule or another atom on another active site. All of these dimensions are very small in nanoscale. So they are considering that catalysis itself, without any external treatment from our side, is a nanoscience. Okay? But still, we some other people say that no, it is not nanoscience. Let's prepare nano materials, and then we are in the nanoscale. Then we are talking about nanoscience. But if we are in the nanoscale, of course, these are the atoms, and these are the active sites, and this is the catalytic or the catalyst surface. Then at this time, we are talking about some, this is the texture of the surface, and we are talking about some microscopy techniques of microscopic techniques or computational techniques or kinetics. All of these can be studied at this scale. Of course, this is very important to understand the behavior or the attitude of the reaction at this scale. If we understand this, then we can monitor and we can control. We can monitor and control the reaction. The other scale is in micro scale. This scale, of course, you prepare some material. If you look at the surface in with TIM or SIM, as we mentioned yesterday, you will see this picture. You will see this picture, okay? But if you just paste or prepare the catalyst that will be used in the reactor, it is not this. It will be in this shape. Of course, there are several shapes of catalyst, several shapes, lot of shapes. The shapes of the catalyst is related to how will you use it, where will you use it, how will you use it, and where will you use it. Okay, this is the shape. If we consider this shape, of course, this is a lens. It is little bit bigger in mesoscopic scale. And in this, the question of interest are how much is the size, how is the shape, and the structure and the composition. As this, in this scale, we can treat a very is larger than nanometer or larger than atomic scale. The other important, and that's what we can see in our with our eyes, is the reactor. Inside the reactor, there is a bed of the catalyst. This is the catalyst bed here in the middle, and the gas flows from up to down or vice versa. It is not important, or it is not our story today. But still, the shape of this brown part is the catalyst bed is determined by our needs, determined by the flow, the fluid which you will use. determined by how much contact time you need, because contact time is important. What is the contact time? Contact time is the time which is spent during the passage of the reactant or the fluid on the catalyst bed. How long it will stay on the catalyst bed. This is the contact time. This is the contact time of the reaction. Okay. This is my macroscopic scale, and this is the real, or not the real, the observed part of the reaction. But where is this part mainly not observed, and this part is completely not observed by our naked eyes. But with some techniques like the instruments we have just mentioned yesterday, we can observe it. Okay, but with our naked eyes we can't observe it. This part is important because in this part you determine how will you use the catalyst, how is the shape of the grains, and the scale is from 1 to 100 1 to 100 nanometers. And finally, this is the real, not real part. This is the observed part in the reaction or of the reaction, which is the reactor. Inside the reactor, there is a catalyst bed, and this is the macroscopic scale. Let's go to, of course, the design of efficient reactor enables these factors. The first one is handling high pressure. It should tolerate high pressure. And I think I mentioned a very interesting story about Le Chatellier when he was on the door of making the reactor which is suitable for the ammonia synthesis, but unfortunately it explodes. So it couldn't tolerate the high pressure of ammonia synthesis. So it's very important to prepare or to manufacture and design a reactor which tolerate high pressure and also tolerate high control temperature and optimized contact between reactants and the catalyst. Usually, when we make cylinder like this, it's a reactor. We use mesh. Do you know mesh? Mesh. It's a kind of a plate of stainless steel or something inert. It's put as a bed for this catalyst, and we use the catalyst over this bed. Okay, this is removal of products. It's very easy to remove products and also exchange the catalyst if needed. Resistant to corrosion, of course, enables optimum use of energy resources. It doesn't waste many energy, and save during operation. Of course, it should be saved during operation. This is the reactor, yes, and we put the furnace or the, if we will use very low very low temperature, we use dewar for nitrogen, liquid nitrogen, which decreases the temperature of the reaction. I think we just finished this part, and this is just combination of these three images. And let's go to the time scale. And I told you we will. There is a lot of shapes of the catalyst, and these are some shapes of the catalyst. It's not all, because everybody is doing or forming these shapes according to his needs, or of course the shape will be different as the needs, and the colors are different because of the composition. All of like this, and this is also this is called the honeycomb, which is used in the exhaust of the mobiles, of the automobiles. Now let's go to the scale, the time scale. We talked about the distance or the scale of how many nanometers. This is the time scale. Of course, you know that some reactions can be carried out in in a fraction of second. It's very small, very fast. However, other reactions may take long time. And these reactions we control or enhance or make a kind of fastening of these reactions by using a catalyst. So catalytic reaction may take in different distances and also may happen in very small time and also may happen in large time or very long time. And of course, some of reactants or catalysts may be used only for few seconds, and the other may last for from 10 to 15 to from 5 to 10 years, for example, in the preparation of ammonia. Now we just finished our this introductory about our talk today, and inshallah, just now I'll talk inshallah about the in-situ FTIR studies. What's the in-situ FTIR studies? As I mentioned in the beginning of this talk, in-situ means you are carrying out the reaction or you are carrying out the monitoring or detecting or characterization during the process or during the reaction. Actually, for in-situ FTIR, it is very interesting technique because it's like as you monitor or detect the peaks like the born of the baby. When the baby is born, you just see it at its zero time. After that, it grows up day by day, month by month, year by year in front of you. This is the same case. It is like, it's very interesting that you see the creation of the molecule on the surface. And you can see how fast it is formed and how big it became. First of all, let me explain a little about this technique. Of course, we use this technique in it is after preparation of the catalyst. We make characterization by these techniques, these instruments like FTIR, XRD, etc. And we may need to check the type of bonds on the surface. The type of bonds on the surface will be determined by using FTIR. We prepare self-support disks. This is the tool, or this is the device, or this is the machine which makes self-support disks. On the left side, it's a kind of, it's called the die, which we add our powder in this die, in this small piece of steel, and we just grind it very carefully and very grind it quietly and add it in this machine. Okay. After adding in this machine, we just press to a certain amount of pressure. This gauge show me how much pressure we have. After that, we take it out. It will be a pellet like this in this plastic bag. This is a machine which we prepare the pellet or the disk for in-situ FTIR. We use self-support. What is meaning by self-support? When you use FTIR, when you carry out FTIR for any to make FTIR characterization, what do? You just take a very minute amount of your sample and add it to KBR. KBR is a material which is used for spectroscopic techniques, and we add this amount of material to KBR in ratio of 99% of KBR to 1% of this sample. Okay, but in this technique, in situ FTIR technique, we just make the whole pellet or the whole disk from our sample. This is called self-support. Okay. This is a not. This is a system. This is glass system. This glass system is working under vacuum. It should be under vacuum, maybe 10 to the power minus 5 atmosphere. Should be under vacuum. Of course, I will not explain about it so much because we use this system, or of course, it's a kind of, this system may change. This type or may geometry or may its design may change, but it has principles, or it has some kind of basics should be there. Like if you have a piece of land, you will build a house. Of course, somebody may make 1 room, 2 rooms, 3 rooms, and but should be there should be a room, at least a room, and should be at least 1 bathroom, and should be at least kitchen, right? These are basics. This is the same. We have main line and the subline and reservoirs and trap for liquid nitrogen and so on. In this system, of course, this is the IR cell. It is very well designed IR cell. This is another shape. This is a system in real. It, of course, as I mentioned to you, this design may be different from a place to another or from person to another, but all will make the same function, and all will have the same properties. This is the IR in a simple form. Of course, this is the furnace. Furnace means it's a heater. This heater is not permanent. This heater maybe we can remove or add. It's this is the furnace, and let me explain here. All of these are in quartz. There is 2 types of or 3 types of glass. The hardest and the most expensive and the most suitable for this purpose is the quartz. The second one is Pyrex. We use this in Pyrex, not quartz, but we use this in, we make this from quartz, not Pyrex. Not all is in from Pyrex, but these windows, which IR beam goes from here, are made from KBR. KBR window. It's very expensive, but this is KBR windows. These windows are made from KBR. Now you are taking vacuum from here, and what is this? This is sample holder. This one. We add our sample here. Sample, which is the disk that I showed you in last slide. This is the disk. It's here, and this disk is like this. The beam comes like this, and red like this. Of course, this is the furnace, how it comes here. Of course, there is a tape, something like tape here, and we just roll like this. It takes this up to the furnace, and our treatment, our gas, our anything will happen. Then we just roll again to come here to the to this part, and we're read by IR. Something like that. You get very beautiful, very wonderful data that you can explain and try to understand where and when you created the new molecule on the surface. I'll show you here. This is one experiment. This is a in-situ FTIR spectra after absorption of CO. CO, which is carbon monoxide, on titanium and platinum and cerium supported titanium. In this experiment, we prepared titanium and added platinum on titanium, then added cerium with platinum on titanium in these ratios that I will show you. Of course, this is titanium. It showed some data, some peaks, and platinum titanium, it showed other peaks. Platinum cerium titanium, it makes modification. Here, I'll not talk about this scientific part of titanium, what's titanium, and what platinum made with titanium, and what is the peaks about which was created after adding platinum to titanium. and what are the peaks or the change of the peaks after adding cerium. Just show you, I will show you the attitude, because if we go deep in these interpretations, it will be useless at this time. Just you will see the attitude of adding something to something and the creation of another thing and how it grows up. These are different samples using the same conditions. But if we, of course, this is alpha and beta titanium 4, and these are parts of carbonated species and the carboxylate and something. Let's go. If we add NO plus CO with the equal ratios on titanium and the platinum titanium, what will happen? Here is the experiment on titanium itself. And you can see some information about, or some peaks about, these are different temperatures, about carbonate and also carboxylate. And these are, you can see here, different species. These are differences between platinum and titanium and the titanium. You can see here that this is on the left side CO2 peak, CO2 carbon dioxide. Carbon dioxide means it is CO has been oxidized by NO on the surface. You can see the at room temperature, this peak at room temperature here. This is very small. By increasing its temperature, became much bigger, and the 200-degree it is very much bigger than before. This in case of using platinum titanium. But in case of using only titanium, what will happen? Nothing. Very small. This is, we don't consider this as a peak, or because it is not due to our catalyst, because there is some CO2 in the gas phase. It may from maybe from air or something, because this cell is still on air, so we don't consider it as a peak. Okay, but this peak grows like this and no peak here. So this is a difference we can see, and how can it become bigger and bigger with time. Also, there is another difference in here. This is for titanium, and but this one, as you can see, it extremely changed with temperature. This is due to platinum, geminal platinum with carbon monoxide. And this is another difference. You can see here, this area doesn't have a change, but this area has extremely changed. I mean, in this way, you can monitor and understand the behavior of the catalyst, of the reaction, sorry. And you can, from this behavior, you can understand the mechanism by time, how it goes and how it starts and how it goes during and how does it end, okay? And this is another experiment. We used here NO plus CO with cerium titanium and the platinum cerium titanium. What is the difference? If we add, in this case, what is the difference? This is the difference when we add platinum to titanium. These are the differences. But what is the difference if we add platinum, cerium to platinum supported on titanium? This is only cerium titanium, and this is, no. There is another one here. Okay. This is the difference between cerium titanium and the platinum cerium titanium. What is the difference here? You can see in cerium titanium itself, nothing. It is like the other case on titanium itself. But in case of platinum cerium titanium, a lot of a change, intense change in the peak. This means it is greatly difference between the three cases. And this is not change. But here, in case of using platinum cerium titanium, lot of it change. This is the in-situ understanding of how to explain, or you will explain better by understanding this data. Of course, there is also some changes here. here is this is grow up with temperature, but this is will little bit changed with temperature. This increased on the expense of this one, and from here you can explain this data. And this is another example. If you reduce the catalyst, this is the reduced the catalyst. The reduced the catalyst means you add hydrogen to the catalyst. The catalyst means your catalyst will undergo reduction with in presence of hydrogen. You add hydrogen gas to the catalyst. It will change the oxidized form or the oxide to metal sometime or less oxidation number. And there is a big change if we use reduced form and or as prepared form. This is as prepared form. It lot of change here, for example, but this is the reduced form. I think from this data you can understand the mechanism where the oxidation occurs mainly by Mars technique or Mars mechanisms that we talked yesterday or day before yesterday, because it uses oxygen in the LEDs. This means CO is oxidized by oxygen in the LEDs and consumated again with oxygen from NO. This means this, okay, because this we didn't have reaction here, but we have good reaction here. And there is another difference, of course, and these are other differences from reduced form and as prepared form. From here, we can say that, of course, this is a third party. And if we use water gas shift reaction, this is water gas shift reaction. CO reacts with H2O, it gives CO2 plus hydrogen. If we use water gas shift reaction, what will happen? Also, we have many difference between the samples together. This is when we use water and we don't use water. When we use water, only this change will happen. This is change. But when we don't use water, this here the changes will happen. I think you can understand here how much the difference between using catalysts to trace the reaction while while the reaction going on. And this is another experiment when we added platinum with zeolite Y. This is the case if we use reduced platinum and as prepared platinum. There is some formate or carbonate species, but here we don't find any change in this carbonate species. Here we can find CO2, little CO2, and this one doesn't have CO2. And these kind of changes you can monitor. And this is when you use CO only with platinum, with iron zeolite. It is very interesting to see the changes here, that there is a shift. You can find why this shift, and this peak grow up and this one doesn't grow up, something like this. You can check the changes. Other experiment, we used CO and oxygen with platinum, and you can check these differences. Of course, it's very clear that there are big difference. If you see this big doesn't grow up very high, but this one is very high. You can understand why this happened, of course. And of course, I think my point is now clear. And this is another experiment of using very interesting part of in-situ FTIR, which is the absorption of some molecules to as a probe molecule. What's probe molecule? Probe molecule is a molecule you use as adsorbent, or you absorb this molecule on the surface to make changes, or you just like sensor. It is like a sensor. If it combines or contact with the surface, it will show you that if it contact with the surface, it will show you acidic side. Or if it contacts with the surface in another way, it will show you basic side. Then you will see the basic or acidic site with this probe molecule. And the CO, when we use the CO before, I show you here. When we use the CO before, from here, you can detect that there is platinum 0, platinum with oxidation number 0 in this area. This is probe molecule. That means you understand the composition of your surface, or the oxidation state of your material. And if you go back like this on cerium, for example, where is it? Here. From here, you can see this. This one is for platinum 0, and there is another one here for cerium 4. So you detect that you have cerium 4, even if it's alpha or beta cerium 4. This is crystalline form. Now let's check this experiment. This experiment is using pyridine on the surface of these catalysts. Okay, it shows this data. Of course, there is Lewis acid site is detected here, and Lewis acid site is detected here, and this is always Brunellested acid site. Brunellested acid site is always being small. This one doesn't mean it is very small. No, its peak intensity coefficient is very small for Brunellested acid site, but for Lewis acid site it's high. This means you have Brunellested acid site and Lewis acid site, and this peak is for both of them are coming in here at this position. Here you can read that you have Lewis acid site and Brunellested acid site by absorbing pyridine on the surface of this your solid material in the in-situ FTIR cell, which was treated previously in the vacuum system, glass system that I showed you before. I think it's clear how much it's important to treat your sample well and absorb some material and trace or follow the reaction, because here we made several experiments. We added we added carbon monoxide. This is as probe molecule. And we added oxygen, expecting that CO will react with oxygen to form CO2. This means the reaction, if we get CO2, this means reaction will happen. If we didn't get CO2, then no reaction will happen. But fortunately, we get CO2 in presence or absence of oxygen, because CO is oxidized by the oxygen in the net. I think we couldn't explain this if we didn't add this make this experiment. Of course, this we already explained, and I hope this part of in-situ characterization or in-situ tracing up or following the reaction is clear. Before, if anybody has any question about this part, it's okay, please. Before going to short explanation about the applications of heterogeneous catalysis. Okay, let's go, and by the end we can have questions if you have.